All right, hey everybody, and welcome to today's webinar, which is Temperature and Relative Humidity in Collections Care. I'm Gillian Marcus. I'm the Preservation Specialist for DHPSNY, and I'm glad that you are here today to talk about temperature and relative humidity in collections. And again, I'm sorry for the music that will probably go in just a moment. So just a little bit about DHPSNY before we get onto the topic at hand. DHPSNY is a 5-year initiative. We're near the end of year 3 now, actually, to deliver essential training and services to New York's collecting institutions. DHPSNY services include archival needs assessments, preservation and conservation surveys, guidance with strategic planning, and access to a variety of educational programs and workshops. DHPSNY is making these services available free of charge to New York-based organizations that collect, preserve, and make accessible historical records and library research materials, and that is you guys. So DHPSNY is a collaboration between two long-running New York programs, the New York State Archives Documentary Heritage Program and the New York State Library Conservation Preservation Program. It was established in 2016 by the New York State Education Department's Office of Cultural Education to ensure consistent and comprehensive services to the vast network of organizations that safeguard New York's records and make them accessible. Okay, so this is a huge topic, and I'm really just going to touch on a lot of these concepts today. So we're going to go ahead and get started. If you have any questions at the end, I'll have time to take any questions that you might have. So we are going to talk about how temperature and relative humidity affect collections, how and why to establish an environmental monitoring program at your institution, tools to monitor the environment, and tools to help control the environment. So today I'll be focusing on recommendations for archival and library materials because the relative humidity and temperature needs of collections materials varies as much as there are different types of material and different objects. So what works for, say, an ivory archaeological item, for example, will be totally different than what is best for a cellulose nitrate negative. But keep in mind, there's no one ideal where temperature and relative humidity is concerned, but rather it's a series of compromises and considerations. So generally, the conservation and preservation community is moving toward a more sustainable model, which is less expensive and impacts the environment less. So rather than very strict parameters, there are more flexible parameters that can be expanded or contracted depending upon the materials in your collection. And we'll keep talking about that. As much as I would love for there to be a kind of one-size-fits-all answer, it's unfortunately a little bit more complicated than that. And it's something that conservators and people who work in collections care are still really figuring out. So I know that you're all here to learn about how to monitor and control the climate in your institution, but I often get asked how we came to determine the importance of climate control on our artifacts. So I thought I'd give you a little insight into how this came to be. And so it is story time. So in the summer of 1940, which was during World War II, the UK began to worry about a German invasion, and the National Gallery in London was bombed about 9 times between 1940 and 1941. So it became pretty clear that the museum's collections needed to leave London. And at first, the government considered putting paintings on a boat and sending them to Canada, but Winston Churchill intervened, and it was decided that they needed to be kept on British soil. So a plan was developed in which paintings from the National Gallery in London would be relocated to a slate mine in North Wales. What were called bungalows, brick bungalows, were built inside the mine to protect the paintings from dampness, dust and dirt, things like that. And the paintings were transported by truck to Wales until the entirety of the National Gallery's collection was stored underground. So prior to the relocation of these paintings, prior to all of those bombings in 1940 and 41, the National Gallery did not have air conditioning. But moving the collection into these mines gave curators a chance to consider what the best environment might be for these paintings. They also spend a great deal of time with the paintings in the mine because, they were sort of stuck in this small village in Wales, so they hung out with the paintings most of the time. And that allowed them to pay close attention to things that they might have missed while they were on display. So while monitoring their condition in the mines, curators noticed that the condition of the paintings was actually greatly benefited from the stable, cool environment. And in particular, panel paintings, which tend to show a lot of stress and strain. So based on this information, the National Gallery was rebuilt in order to control the climate, including the installation of air conditioning. And this was a pretty big turning point for how collections staff began to understand the importance of the environment on collections care. And a great deal of this knowledge was gained from examining the paintings before, during, and after they were in the mines. So if you're interested in this more, there are some really great articles, and I think at least one documentary on this. And also the National Gallery is a great place to visit in London. Okay, so we are moving on from story time. So I'm going to be referring to 3 categories of environmentally induced decay during this webinar: biological, chemical, and mechanical. These are often interrelated. For example, biological damage such as mold growth will often also cause chemical and mechanical damage. Chemical damage will usually weaken an object, which results in mechanical damage. So, these things are all interrelated. You rarely have one without the other. I'm going to talk about biological damage. That refers to things like mold growth and pest-related damage. The most common example of biological damage as a result of environmental issues is mold growth. And mold risk increases at 65% relative humidity or higher. The likelihood that mold will grow increases at 75% or above. So we'll talk about this a little bit more later, but that's probably the most common example of biological damage that you'll come across. Mechanical damage as a result of the environment often occurs when material is stressed due to fluctuations or extremes in relative humidity and temperature. So here are 2 examples of environment-induced mechanical damage. The top is a cellulose acetate negative. I'm sure many of you have seen something that looks like this in your own collections. This type of damage is called channeling or delamination, and it happens when the acetate base of the negative shrinks, and this causes tension against the gelatin layer. Vinegar syndrome exacerbates this condition, so this is really an example of both mechanical and chemical degradation. Mechanical damage can occur as a result of high relative humidity or low relative humidity, or fluctuation between the two. At high relative humidity, adhesives can soften, organic materials expand, and at low relative humidity, materials can shrink, stiffen, and become brittle. Fluctuation between the two can result in stress on organic material as it expands and contracts. And the illustration below gives an example of a wooden board, which shows seasonal fluctuations in relative humidity. Chemical degradation includes damage which results from the acceleration of existing chemical degradation processes or the introduction of new factors in the environment which damage objects at the molecular level. Some examples of chemical degradation processes include newspapers yellowing and becoming brittle due to acid hydrolysis, red rot on leather-bound books, and cellulose acetate releasing acetic acid during what we call vinegar syndrome. I'd like you to keep these 3 types of material damage in mind as we talk about the variables in the environment of your collections during the course of the rest of this webinar. So I'm going to talk about relative humidity and temperature in collections and look at some of the ways that they affect materials. Relative humidity is a variable which can be confusing, but it has a huge effect on the well-being of your materials. One thing I do want you to keep in mind as we're talking is that temperature and relative humidity are interdependent, and the effects of one are not felt without the effects of the other. So although I'm breaking them up to introduce each factor, they are inseparable from one another. So please keep that in mind. It's probably easier to discuss incorrect relative humidity than it is to discuss correct relative humidity, because the ideal relative humidity for each object is essentially is different. There is no ideal, relative humidity or a magic formula I can give you. But what I can do is explain kind of what you don't want to give you a better idea of what you do before we talk about general guidelines. So when I talk about incorrect relative humidity, I'm talking about one of three conditions usually. A relative humidity of 75% or higher, or what we would consider damp. A relative humidity which is above or below a critical value for a given object. And fluctuations in relative humidity in which affect the object stored in a given climate. And also as a side note, I have uploaded I think 5 handouts on storage guidelines. That's like environmental guidelines for storage, monitoring temperature and relative humidity, some limits from the Image Permanence Institute, a data logger quick comparison chart, and the National Park Service Museum Environment Guide. And you can download those from here. Those are some materials which are really helpful to have and to consult. Okay, so generally speaking, for most archival materials, dampness and high relative humidity are the most potentially damaging environmental issues. RH, which is too low, is more likely to cause damage to archaeological items, for example, paintings, and materials that have multiple layers. Fluctuations in RH are often even more problematic for archival materials than consistently low RH. So going back to this idea of dampness or 75% RH or above, starting at 65% RH or higher, mold risk on many objects increases, and this risk jumps even more above 75%. Where all things being equal, this dampness is likely to result in mold growth. And that's why we keep an upper limit of 60%. It's what we generally recommend for storage to prevent most mold growth. And it's a bit lower than that 65% and that 75%, but it's just an extra bit of insurance there. Some negative effects that can occur when RH is consistently too high for an object or a type of material include metal corrosion, glass grizzling, bleeding dyes on textiles, bleeding watercolors. Dye-based digital prints can bleed in high humidity. You can see an example of that in this photo here of the pink line. It looks almost like it's been exposed directly to moisture or to water, but that's actually just high humidity. Photographic prints can often block together, which is when they become stuck to one another, and they can be really difficult to remove without damage. And the expansion and contraction of stretched canvas can be problematic if it causes tension between the paint layer, for example, and that canvas support. So high relative humidity is something we want to avoid for most of our materials. On the flip side, RH, which is too low, is generally less of an issue for archival materials. It's a pretty big issue for a lot of objects, three-dimensional objects, archaeological objects, furniture, things like that. Parchment and vellum tend to actually be pretty sensitive to low RH. You can see in that photograph there on the left, at 50% RH, that covers almost flat. And on the right, the 20% relative humidity is causing that vellum to contract, and that's pulling the book cover up into an arch. And parchment and vellum are, their skin, basically. If you think of your own skin and how it reacts to humidity outside and how it gets dry in the winter, things like that, that's what causes that issue. So if you do have a lot of parchment, if you do have a lot of vellum, that's something to keep in mind. It does have, it has a higher sensitivity to fluctuations, relative humidity, and to very low relative humidity. But in terms of paper and photographic materials, they are, in general, a little bit less sensitive than some archaeological materials, for example. So fluctuations in RH can cause wood to crack, split, or delaminate. Paper adhered to stretchers can tear. This can be problematic for photographic material with a layered structure, varnish maps, anything that has a structurally complicated makeup or multiple layers of media can be affected by fluctuations in relative humidity. Things like glass are affected. You can see in this photo that the blue beads have begun to crack and some of them have fallen off. That's an example of glass disease that's been caused by pretty severe fluctuations in relative humidity. So we're going to look at temperature now, but again, please keep in mind that temperature and relative humidity are interdependent. And also, the image there is melted wax figures after a fire at Madame Tussauds in 1925, and it's absolutely terrifying. So you're welcome. Okay, so as with relative humidity, temperature can be problematic when it's too high, too low, or there are fluctuations. Luckily, you do have a little bit more leeway when it comes to temperature ranges for archival materials in particular, and that's good. So for archival materials specifically, high temperatures are the most problematic out of the high-low fluctuating possibilities. High temperature causes acceleration of existing chemical degradation processes that might be occurring anyway. And that includes things like, again, deterioration of newspapers or other poor quality paper, which might be problematic. That high temperature really kind of puts the accelerator on those chemical reactions. So it can, again, to go back to the example of newspapers, since we just did a newspaper webinar, it can cause this poor quality paper to become more acidic, brittle, and yellow. High temperatures can often soften adhesives, emulsions, and some paint, which can result in damage to an object which has been, for example, repaired or had materials readhered, particularly with glues that can become soft, excuse me, closer to room temperatures. An example might be, animal glues that have a protein base. Plastics can become brittle and sticky. They can disintegrate in other ways when they're exposed to high temperature. Polymers can become softer, particularly if they have what's called a low glass transition temperature. And I won't get too much into that, but the lower a glass transition temperature, the softer something is likely to be at room temperature. And conversely, if they have a high temperature, they usually stay pretty hard, until the temperature gets very hot. The toner layer on a photocopy, for example, that's an example of a polymer which can become softer as the temperature rises, which can then cause it to offset onto other materials. So if you've maybe had like a binder or that report cover plastic that you've had photocopies in or computer printouts, and maybe they've stuck to that plastic, and when you pull it away, you can actually see that the ink, the printing ink on there, that's an example of something that can be caused by elevated humidity, or excuse me, and elevated temperature, either one. Magnetic media, audiovisual materials are pretty sensitive, and those can disintegrate and become unplayable. Do you remember kind of what happened? What used to happen if you left videotapes and CDs in your car in the sun? That's kind of an extreme example of what high temperature does. But again, audiovisual materials are pretty sensitive. Cellulose nitrate and cellulose acetate can shrink, distort, and crack, as we saw earlier. Cellulose nitrate in particular can combust if it reaches high temperatures. It's pretty dangerous in that way. And cellulose acetate releases acetic acid as the temperature rises, which causes what we call vinegar syndrome. And I'm sure many people listening to this have experienced vinegar syndrome in your own archive or library. And you can actually smell that acetic acid in the air. That's really often accelerated quite a bit by high temperature. Low temperatures, fortunately, are not terribly problematic for books, paper, or photographic materials. And in fact, low temperatures can slow down some of those chemical reactions that heat actually speeds up. And that's a big reason why we recommend cold and frozen storage for photographic materials and for some AV materials. Low temperatures can be problematic for paintings, varnished objects, some glass, some archaeological materials, a lot of three-dimensional objects. If you have a low temperature but relative humidity is in an acceptable range, you're doing pretty well where our archival materials are concerned. So that is one thing that we're fortunate in caring for our library and archival collections. Low temperature usually is a good thing as opposed to a bad thing for paper, books, and photographs. So there's one other thing that you should be aware of, and that is dew point, which is the temperature the air needs to be cooled to for relative humidity to reach 100%, which is the point at which water vapor begins to condensate out of the air. And obviously that's something that we don't want in our collections. So at a constant dew point, when temperature increases, relative humidity decreases. And when temperature decreases, relative humidity increases. So that means that raising or lowering the temperature without accounting for dew point can lead to incorrect RH levels, and it can create a risk of condensation. So the dew point is kind of a complicated thing to explain, but there is actually a very helpful online tool which can help you to use this information. So Image Permanence Institute has this dew point calculator. It can be found on dpcalc.org. And essentially you can enter the temperature and relative humidity values that you're getting from your data loggers, for example. You can enter that information into the dew point calculator, and it can show you what your dew point is. So it's not something that you need to calculate yourself. And after it gives you this value, it will then show you in a preservation evaluation panel what kind of risk you're facing with your current values in terms of temperature, relative humidity, and dew point. So it's a really, really handy tool to have. It's free. It's available online. It can help you understand some preservation metrics, including natural aging, mechanical damage, mold risk, and metal corrosion risk. And it's a really neat tool to have if you are able to access that data for temperature and RH. And I can't recommend it highly enough because I'm not particularly amazing at math, so this is very, very helpful for me. And I think it's helpful for a lot of people who are in charge of monitoring the environment and collections. So by now you might kind of understand why it's so difficult to find or explain an ideal RH or an ideal temperature for collections, because different materials respond better or worse to different environments. And this is something that collections care and conservation staff really struggle with, and it's also why we take steps to make certain climate control measures available for some materials. For example, recommending cold or frozen storage for photographic materials and digital prints. But no one has one type of material in their collections. So we generally come to the conclusion that for mixed archival collections, rather than having a specific set point, you have a range that you try to work within, and that's 59 to 77 degrees Fahrenheit and 45 to 55% relative humidity, plus or minus 5%. So these are acceptable parameters for mixed archival collections where materials are generally in good health. Photographic materials are another matter altogether because they're incredibly sensitive to changes in RH and temperature. There are a lot of variables, so I have uploaded the Image Permanence Institute's Media Storage Quick Guide, which is great and very thorough. And you can have a look at that because they're really the experts in this type of media. But generally, you do want to keep RH between 30 and 50%. So generally, film and photographic materials are more stable the colder the temperature is kept, which is why we often recommend cold or frozen storage for photographic materials. And again, the IPI Media Storage Quick Reference Guide is really helpful with this. So now that we've talked a little bit about how various temperature and RH values can affect materials, I'd like to talk a little bit about establishing an environmental monitoring program at your institution. This is a super important step toward getting control over the environment your collections are stored and exhibited in, which in turn is really one of the most important things you can do for the health of your collections. Really, if there's one thing you can do that can have a huge amount of impact, it's getting a handle on those environmental parameters in your collection storage areas. Establishing an environmental monitoring program and having the discussions needed to do so are really valuable steps toward getting your institution or department on the same page, having a document to refer to, and gaining institutional support from the top down. Recording institutional knowledge is also important so that if you, with your knowledge of how the environmental monitoring program is run, should leave the institution for any reason, then someone else can continue to take care of the collections. So it is so important to make sure that you write down any kind of environmental guidelines that you come up with. So some questions to ask yourself, to ask if there's a committee that's dedicated to coming up with these answers, if you have a full collections care team. Some things to consider when you're establishing an environmental monitoring program include what are you using to record data? Usually this is a data logger, which we'll talk about in a bit, but maybe you want to think about what kind of data logger. Where are you recording this data? So which storage rooms are you going to be recording data in? Ideally, it should be all of them, but are you going to use multiple loggers in a single room? For example, if there are any odd pockets of condensation in a storage room that should be monitored in addition to a general reading, that might be something you want to think about. If there's a particular area where mold tends to grow, you might want to think about that, monitoring that in addition to a kind of a general room read. You want to think about how often you're collecting this data, whether that's once a day, once a week, once a month. As long as you're doing it regularly, that's what's most important. You do want to think about how you're going to track this information, whose job this falls under, whose job description. So you ideally want to assign this task to a particular job or particular position, because otherwise it can kind of fall to the wayside or through the cracks if no particular position claims ownership. And it's not through anyone's fault, that just sort of happens. And finally, you want to think about what you're going to do with this information. So how you're going to track it, or, whether you're going to make charts or graphs, what you're going to do with those charts and graphs. And you want to think about how much past data you should keep track of. And there's no real wrong or right answer to any of these questions. Wait, actually, I should rephrase that. There is definitely, there are right answers, but it's flexible. So each institution will be different. The most important things you want to keep in mind are consistency, frequency, and actually analyzing the data that you do record with those data loggers. There are lots of different variables, and you need to decide what works best for your institution. A lot of the time, staff at institutions without HVAC systems will ask me if they should even bother recording, since they feel they can't do much to control the environment, which I understand. But the answer is yes, of course, and maybe even more so if you don't have an HVAC system. It's really crucial to know what's happening to your collections because it allows you to allocate resources toward areas that have the highest need. And funders like to see institutions that gather and record data on their climate because it shows investment and awareness. The point is that you're taking steps to be consistent in your approach. And that's really valuable. So in terms of tools for monitoring the environment, thankfully you do not have to use this device here, which is very beautiful, but seems quite complicated. Excuse me, for this webinar, I'm going to focus on data loggers rather than some of the older tools used to measure the environment for a couple of reasons. One, they can be really complicated to use, which discourages actually using them at all. And also, they're often strongly affected by user error. And this can be true for data loggers as well. But they're becoming so inexpensive these days and require minimal calibration. They're really designed to be used by people who have a minimum of experience, and that's really important. So I'm going to focus just for a bit on choosing a data logger. I've uploaded a guide to low-cost data loggers from 2018. It can help you narrow down what you're looking for and how much that might cost. And it doesn't cover every type of data logger and every model, but it's a good reference to have. So, if you do have whirling hygrometers and thermohygrographs, those are great too. But there's less of a chance of user error using a modern data logger. So just a quick note, even if you have an HVAC system that does monitor temperature and a relative humidity, which is most modern systems, you still need to have independent data loggers for many reasons. They can catch system failures. They can confirm whether the HVAC sensor is actually giving you accurate information. And they can monitor pockets or areas where the sensor isn't going to give you specific information. For example, if you have an area of a room that you're concerned about, the HVAC sensor isn't going to give you a specific reading for a specific part of a room. But if you do take a data logger and put it in the area, you can get a kind of more of a pinpointed reading. So that's something an HVAC system just can't do. Data loggers can be set up to automatically gather data at set intervals. Newer models can text you. They can send information wirelessly to your phone, which is great for after hours, things like that. Programs that come with data loggers can help with charts and graphs and visualizing the data. I believe the guide to low-cost data loggers covers which models come with software. Some common types of software are the eClimate notebook that comes with the PEM data loggers. I believe Onset has software. I'm sure that more and more of them actually sort of come with software attached. So visualizing the data, charting your findings can really be as simple as an Excel spreadsheet or even a Word document that has columns for time and date, RH, and temperature. It can be as simple as that. It can be a worksheet that the values are handwritten into. That's fine too. Using a chart to actually visualize trends is really helpful. And recording data through an Excel spreadsheet or through a specialized computer program can make charting and graphing this data really easy. It does it for you automatically. And that comes standard with a lot of data loggers. But even if it's as simple as writing things down in a notebook,
please press any key on your phone to remain in conference.
Oh. Not sure if everyone can hear me. I just got a message about my phone. Yeah, it can be as simple as that. All right, great. People can still hear me. So where were we? Okay. So there are several climate control solutions for collection storage, which I'll just touch on briefly. Obviously, the most common is a central HVAC system, which is great if you have that. There are also standalone dehumidifiers and window air conditioners that can be used as supplementary climate control devices. Fans can help to improve airflow in spaces, just the fans that you can get, at Walmart, CVS, whatever. But even something as simple as sealing windows with film and keeping doors shut can actually help to control that climate. Every little bit helps. Pardon me. Passive control is becoming more common as institutions try to become more sustainable and have less of an impact on the environment. The most common methods of passive control include designing buildings that are specifically suited for the local environment, which can help to control those fluctuations through the way that the structure is designed. A similar method is to correct existing design faults in an institutional structure. So pretty much everyone I would have met, I would say in New York State, is in an institution that they will be in for the next few years. They're not planning on designing an entirely new structure. And so architects can modify existing structures in order to help correct design faults, which increase in reliance on HVAC systems. Obviously, neither of these methods is cheap, but they can help to save money and energy over the long-term life of the institution. Other passive control methods include constructing cases, enclosures, and microclimates for very fragile objects that have special needs. And an example of this is putting a very fragile or valuable document in a sealed package, excuse me, which creates a more stable microclimate and mitigates fluctuations in response to external situations. So at the most basic level of passive control, we're talking about a situation with no moving parts, no machinery, and no energy consumption at all. And in terms of building design, that means ensuring that there are reliable walls, a strong roof, sealed windows, and doors that have good vapor barriers. In new buildings, low energy designs can be explored. Buildings with high thermal mass, high insulation, high air tightness. Structures like that have been used by some recently built museum structures. One easy thing you can do is to identify and eliminate any sources of damp, which is a good thing to do anyway. That helps to prevent mold. You can use bags, envelopes, or encapsulation on objects that are vulnerable to incorrect relative humidity or fluctuating relative humidity. Transparent polyethylene or polyester are often used. Those are pretty reliable. And you can use simple cases on the most sensitive and valuable objects on display. Stefan Michalski at the Canadian Conservation Institute has done a lot of research on this, and you can find information by searching for his resources online. He goes into a lot of detail talking about variations in relative humidity, variations in temperature, and how to control those things without a reliance on HVAC systems. Okay, so I'll take any questions you have now. Thank you for your patience. I know it's been kind of a glitchy webinar. I think questions are coming.
Please press any key on your phone to remain in conference.
Okay, so that's a good question. So someone has asked, can you talk a little bit about how previous exposure to flooding for paper-based and other items may or may not affect acceptable ranges? That's a good point. If material has been exposed to moisture in the past and it's suffered physical damage as a result, for example, if it's become weaker, if it's had any kind of mold growth as a result of exposure to moisture, that would sort of lower the relative humidity that things that have been moldy in the past, things that have physical damage tend to absorb water more readily. So that means something that may have been tolerant of a slightly higher relative humidity in the past might be more vulnerable to that, particularly if you do have mold growth. Does that make sense, Greta? And Nicole's asked, is it possible to have these slides sent in an email? Yes, we do send out the webinar along with, I believe, the handouts in an email following up. Oh, and Marissa's just said that. Are there any other questions about temperature, relative humidity, climate control, Welsh mines? Let's see. So are there any types of collections that require radically different atmospheric conditions from other types? Pardon me, I'm sorry. Um, Photographic materials are a good example. Um, they are, in terms of atmospheric conditions, actually, maybe I'm misunderstanding that. Um, I'm taking that to mean temperature and relative humidity. Okay, okay, good. I thought suddenly maybe, sort of like space or something like that. Mostly photographic materials, they're a lot more sensitive, and audio-visual materials. Those tend to need a lower relative humidity and a cooler temperature, much cooler temperature, generally speaking. And that's why we have things like cool, cold, and frozen storage to designate those type of tight storage parameters. Trying to think of other things that have Um, let's see. That's probably the example you're likely to come across most, especially when dealing with archival and library materials. Let's see. So, what are your thoughts on the use of desiccants and how to select type and quantity? That desiccants are almost their own webinar. That's a good question. Those are better if you have an enclosed space. If you have, for example, a case where you have a if you have an item that is very sensitive to fluctuations or high relative humidity. Linda, if you email me directly, and if you have a particular material that you have in mind, I'm happy to send you some material specifically about that. Let's see. Jennifer says, can you discuss in more detail what you mean by fluctuations, big swings, small changes? That's a good question. Typically, the current thinking right now is that you want to avoid more than 10% change in relative humidity in the course of 24 hours. Um, some materials can take more than that. Some are sensitive to less than that, but generally you try to keep that RH within 10% over a 24-hour period. That's by no means specific, but it's a general rule of thumb that we try to keep in mind. Let's see. What are some ways you can create microclimates for specific items like
Please press
vellum?
any key on your phone to remain in conference.
One example is a sealed package, which is you have some sort of glazing on the front, you have the object, you have molecular sieves or molecular traps, for example, zeolites, and you have that in microchamber paper. So those are molecular scavengers that, in theory, remove some of that pollution from the air, some of those acidic byproducts. And then you have the back is sealed with what's called Marvel seal. So you create a very small microclimate that slows down those external fluctuations. And that's often used for items that are then going to be framed. Um, so I know we've done that for parchment. Um, Even something as simple as keeping it in a box, it helps to mitigate some of those fluctuations. A question about fluctuations in temperature and relative humidity. How quickly do these changes have to happen in order for them to have serious effects? For slowly changing from a warm or higher RH in the summer to a cool or lower RH in the winter, is that an issue? Um, Not necessarily. That is kind of what happens between the seasons, and one perspective people have is something called proof fluctuation. So say you have a panel painting and it's been exposed to the biggest kind of swing in its past that maybe caused it to maybe cause cracks. In theory, as long as fluctuations don't hit that level in the future, it's not going to develop any more or any worse cracks. I don't know if I'm explaining this clearly. And that's called proof fluctuation. Um, so most things that we get that are historic, they have been through seasonal changes. You know, I don't think that it's going to necessarily cause any more damage. Um, and then this is in terms of like seasonal fluctuations. Now, if you're getting the same temperature, you know, vast temperature and humidity differences within the course of a week, that's problematic. But over the seasons, I think that's normal. And I think everyone's trying to move toward, as we move toward more sustainable climate control, you know, we're working toward accepting those fluctuations as something that happens. Hopefully that makes sense. Um, if you have further questions about proof fluctuation, I'm happy to provide more information about that. Stefan Michalski, who is with the Canadian Conservation Institute, he writes quite a bit about proof fluctuation, which is something, you know, it's a great concept that something, once it receives sort of the worst, in theory, unless things get to that point again, it should be fairly stable. But obviously, we do want to try to support a consistent temperature and humidity when we can. Does anybody else have any more questions, or you guys good? So if you do have questions, you can always email me at gmarcus@dhpsny.org. I'm happy to you know, look at more material, send you something that you're interested in knowing more about. Not a problem. But thank you guys for bearing with our technical issues. And all right, great. Thank you, everybody. Have a good afternoon, and hopefully the weather is as nice for you as it is in Philadelphia. Take care.